we're going to have a pretty decent overlap of the pulsed RCF signal that's going to go into this device. At least that's what I'm hoping. 4 sets of 4 coils that are doubled up, and this should give us the best chance of getting as much RCF out of this device as we can. I'd rather split the difference on the load matching than to have a wider pulse where natural gravity could come in and strip away our RCF. We had this all torn apart and we remodified it now so that it's not going to be a 440s to give us 10 ohms. Now we have 16 10s, which gives us 0.6 of an ohm, which is pretty awesome. We are pretty darn close on the load matching, and that's about as close as we're going to be able to get for this test. But I still have to build the bridge rectifiers, so what I'm hoping is to have about maybe 3 volts coming out of the device, maybe 350 3.5 volts, and then for this coil, right, and then out of the high voltage side that we're going to try to run, I'm going to try to go with well, some calculations that I had. One coil was 13.5 volts through a diode, so I don't know, 108 volts. And then what we can try to do with that 108 volts is put it into a capacitive device and see if we can even shield gravity with it. You know, assuming this is going to work at all, right? But I mean, the devices will be rotating, so we do know that it has centrifugal force going right through the coils right at the time of conception that the energy is being made. Like if there's any time to combine the RCF with the device, that's the time to do it, right at conception, right? Because you take a look at like any audio device, a microphone for example, the coils on a microphone, you're just creating the electricity. It's like a small little AC generator actually, and what it does is it just takes the voice that's in there, converts it to an analog signal, and then we just of course take that signal and boost it and of course send it wherever we want or store it, right? Anyways, that's it for October the 18th 2018. Hello, it's October 27th 2018. We got some more work done on the project. I made up these little diode bridges. They should be good enough. These diodes can handle an amp each, so it should be good enough for what we're going to do. And I made up 4 groups of them. Hello, it's still October the 27th 2018. We were able to tie together the low voltage side, so we have our bridge rectifiers on here. It took a lot longer than I thought to get this all wired up, but I had to go slow and make sure it's done right. So basically what we'll do is we'll take the DC coming off of these rectifiers and we'll tie them all into these 2 top slip rings, and then we can export them out that ways and then do tests and see what we figure. But I still got to do the high voltage circuits, but that'll be maybe tomorrow or Monday. We'll just see how it goes, because boy, the day just flew by today. Anyways, that's it for October the 27th 2018. Till next time, bye bye. Hello, it's October the 29th 2018. We got some more done on the project here. We have all the bridge rectifiers all tied in now. This is a low voltage one, and this is a low voltage one here too. And what do we do with the high voltage one? I know we taped over it. It's over here, it's underneath here. It's underneath here, the high voltage one. Yeah, I got it taped down pretty good, so because when this is spinning I don't want it to come flying off there, eh? And I was able to find a test device over here. See if I can find what a mess. I got stuff all over the place. So let me just see. There it is, right here. This was a device that I made a few years back. What it basically is it's stacked capacitors. I got 6 of them, actually 1, 2, 3, yeah, I got 6 of them, even though there's 7 plates, because there's 6 gaps in between the plates. and they're all pretty close to being the same distance apart, and the dielectric in them is all the same. So I'm going to try putting the high voltage on one of these plates and see what happens, and then I'm going to also, with the correct polarity, well, they're already kind of wired for it, so I'll just hook a high voltage up to all 6 of them, and then we'll see if we can shield gravity with it. What I'll do is I'll charge a high voltage up on it and put a coin on it, and if the coin floats, then it should be awesome. But at least that's the theory anyways. It's smaller than what I was hoping to test with, but should still work good enough. I'll double check it and make sure it still is an open circuit. It's been bouncing around in toolboxes and stuff for a while, so I'll make sure it's still good. Hello, it's October the 30th, 2018. We got the generator all done up. We got the magnets installed. So make sure those are all good. They're looking pretty good. And I got it wired up over here. We got the low voltage side going to the RCF coils. And then of course the 12 volt feed is going over to our dump coil, which looks good. And I had the switch configured like this, but that's the wrong polarity. This one is the generator, this one is the grid. So we're going to start it up, and we didn't have any results. The engine wasn't running, but I want to check the voltages up there and see just what we get for voltages. Wait for this thing to focus in. So here we go, we'll start it up. Okay, so we're going to go direct off the high voltage side, and we'll see what we get now. And I'll start it up. We do like 108, but 153 is pretty good. So I just had the polarity on those backwards. So the white one is actually the white one is the positive one. So that's pretty awesome. So it shows that at least the principles of generating power are far better with a 90-degree plane as opposed to a 60-degree plane that we did the V-Gen with, which this is just awesome. 153 volts. So I'm gonna see if I can hook that up to our device here. We'll see if we can shield gravity with this darn machine. I'm gonna measure it up and see if we have any shorts on it or not. Hopefully it won't be shorted out. Okay, it's still October the 30th, 2018. So we tested the low voltage side, and it wasn't producing any RCF extraction that we had hoped. We were able to produce 2.5 volts, which is pretty decent, pretty much what I had predicted, because, well, it just stands to reason. And then I set this on here, and if we were shielding gravity with this device, I mean, we have the RCF force is there, right? You can see that it's spinning, so the force is there, and the coils are there, and the magnetic fields are there. We have them going through diode bridges. I'm going to turn this off. We have them going through a diode bridge already. So, unless the diode bridges are actually stopping the power from going through, because we did full wave rectify them, all of them, right? So by doing that, we may have inadvertently destroyed the RCF signal. So I'm gonna flip this one over now. Yeah, so we'll set it up like that and give it a try. This is now just flip it over. Fell off. So what it should done was just floated above, right? I actually can't feel any difference in gravity above it. So, get electrocuted here. That is 108 volts DC. Set up now. Yeah, see, it just vibrates on there because of the vibration of the machine just rotating. But we flipped it over both ways, and we don't have any RCF transfer whatsoever. So basically at this point, the only thing for me to really do, which would just prove it hands down, would be to go a half-wave rectifier, and we take it off each side, because if the diodes, well, they're not even warm, which is actually good. I can't find either. Yeah, these ones here. Those diodes aren't even warm, which is pretty awesome, which means that the circuit isn't being overtaxed. So at this point, I'm just gonna have to go with a half-wave rectified system. That's going to give us our best chance, our best chance to get the RCF out of this device. I mean, it's there. The centrifugal force is there, right? Like it has to be. The device is rotating. The coils are being bombarded with RCF. They're going through a magnetic field. There's a voltage on them. If there's voltage on them, there has to be current on them. You know, some, at least enough to show on the device that there's voltage. So yeah, that's the best thing we can do. And as far as the high voltage side, we will still have these are the high voltage coils right here, a south, a west, an east, and a north. That'll be one phase, and then we'll just go with a 4 and a 4. So we'll half-wave rectify it, and then when the next set of coils comes in, half-wave rectify them, and that's allowing natural gravity to jump in and strip away what we if we are actually transferring it. Natural gravity is just bombarding everything all the time, right? So it's a risk, right? You know, the only real way to prove it would be to actually fill all the gaps in this device with coils, so that we don't have a chance for natural gravity to strip away. See, like if we go from this coil to this coil, right? As this one's dropping out, this one's coming in, right? So I'm just wondering. Well, we'll try it half-wave rectify the way it is, the way it's already put together, and then worst comes to worst, we got these all doubled up. We can separate them and split them even further, so that we have, like, put another one in the middle center of this gap, in the center of this gap, like beside this one, the center of this gap all the way around, because we got 16 doubles, so we can go with yeah, we can go with 32 loops if it came to that, and then half-wave rectify those. That's the only thing I can think of now to get it off, get at least one side of the circuit away from the semiconductors, right? And then that way we got a raw signal coming right out of the coils. It's consistent. It would be it'd be pretty good, but yeah, I'm just thinking right now. I'm not surprised that it didn't work. A little bit disappointed, but when we're trying to do something new with electricity and electronics, and we have these semiconductors which work with, which have been working with electricity since forever, how do we know if it's not going to filter it, right? But if I set it up in a way that that we have a clean signal coming right in with no semiconductors and nothing to filter that signal, we just might get this darn thing, But that is pretty awesome that we got like 150 volts or so on the high voltage side. That was more than what I had hoped. So I was thinking we're going to get 108, but that was pretty decent. I just wish I had more money to buy more coils, right? Because with this design, we got lots of room underneath here to put more loops, and lots of room up top. And it'd be awesome to just fill all of these cavities. Like we got 32 here and go 4 times that. So then we could go with 64 128, right? To have 128 loops of half wave rectified RCF. That'd give us our best chance.
Thanks for listening to Focus on the Family. Let's resume now with the balance of today's program.
Yeah, I might have to. Well, we'll go with the half wave, just for a quick, right? Do a quick check on it and see. It's the easiest to do, and it's not a major rebuild. I'll go with the half wave rectified, just for a test. Get one side clean, and then worst comes to worst, we take the high voltage coils out and we unwind them and make another 32 of these coils, the low voltage, and we put those in between and fill in this gap. And then we go half wave rectification with those coils, which would be, boy, that would give it, well, it would look similar to what we have here, right? Because we'd have, as this one's leaving the magnetic flux density, I'll show it like that a little bit better. This one's already like halfway through, and then it would just be, it'll be a pulsed half wave rectified RCF current, and that might be the better way to go. And we could just take these diodes and reuse them, and it wouldn't be that hard to do, because for each group of 4 we have as south, west, east, and north. We use one diode on those. Tie those all in parallel, polarity observed, and just go one side with a diode. And we already proved that a north, south, west, and east set of coils going through these diodes aren't really cooking it too much. Like they're not smoking or they're not burning up, and we have it load matched for maximum efficiency. So there can't be much current going through them if they're not even warm. So one diode should be able to handle it. If they were warm, then I'd be concerned, but they're not even warm when we were running it there. So yeah, I'm just thinking about some stuff right now. And as much as it would have been fun to go with the gravity shield at this point, because basically the whole idea for the gravity shield is, if we have the power and we can get the RCF out of the device, the RCF can be put into a coil to push, like a thruster to push the piston down. But now if we take that signal and we go high voltage with it, so now it's a capacitive signal, and we charge with a capacitive flux density between these two plates to get a flux in there with an RCF component to it, then the natural gravity pulling from the earth would actually disappear from everything above the device, right? That's sort of what it would have to be, because you're actually just cutting off the source of the gravity when the gravity comes from the mass of the earth. So everything above it would be weightless, which of course would, the air that would move down into this area would then start to move up, because the other air around it would be pushing it, right? Sort of like an air bubble in a pool, right? The bubble always goes up because the water underneath it is pushing it. And it's just a simple little test, and it was a lot of fun to do that. I may just snip one of these, because we might not have enough voltage to power. I got 6 of them there. I might just do one more test and just power one of these caps instead of 6 of them. And we did test them, and they were at 6 meg, so at least we know they're not short circuit. But I don't know if capacitance is a factor or not, because this is brand new, right? Not that I know all that much to be able to figure that anyways, but I'm going to try that test. I'm going to cut all of them away except one, and then we'll try it again and see if maybe we just didn't have enough power to power 6 of them, and go from there. So I'll try that and then come back to the video. Okay, so what I did was I just left one set of plates tied, these center plates. So we're going to charge this one set with 145 volts. RCF signal comes through. If I put a bolt on the top, it should just kind of float up, because we shut off the gravity below it, right? So let's start this up. Actually put that on his switch a long time ago. I'm gonna flip it over now, and we'll try this again. Yeah, gravity's still getting through. So it was a lot of fun. That's all we can do for today. That was a blast, actually. So it takes me a week to fix it all up, or longer, and then the test is done like in 15 minutes, right? So yeah, that was fun to try that out. At least now we know we got some decent voltage on it. So I'll just kind of show you how this works. So we got it on this here black one, comes down here and goes over to the grid, right? This black one comes over here, and it goes over to our plug-in behind that styrofoam there, and comes in over here. And then we got I'm gonna be careful I don't touch that. This one here switches our neutral, and this one here switches our hot. So what we did is we brought the grid in, and the grid is coming off of this side of the switch. And then what we did is we taken this one here, which comes from the generator, and it goes off of this side of the switch. And then this plug is then wired through off of the common on each of these. So we have a hot and a neutral, and then of course the ground is all tied. All the grounds get tied together, because that's just switch 2, right? I mean, it doesn't matter if the grounds can be all tied together. Actually, they should be. Then everything's all apples and apples, right? So anyways, I'll start this up. And whoops. Now when it's up and running, and if we get this thing going, right, because all we do is break make, right, and then that shuts, because it breaks the circuit with the grid and makes the circuit with this one here for the genset. And if we can do that and get it actually self-supporting itself, and then I can unplug this grid, the grid was just uses to start it, that'd be awesome to be able to do that. That's my end goal. But I'm gonna unplug this. I don't want to have that plugged in, because it's kind of open there. I still got to get a cover plate for this, and I know to be careful to not be touching anything. So that's a lot of power in there. It's 15 amps coming through there, so wouldn't be good. But it is on a ground fault interrupter as well, because that plug comes across, goes over to the garage door opener, comes down over here to that plug, over to this plug, to the outside plug on the load side, and that's a GFI plug. So we are protected somewhat with the circuit, right? That was very educational, and it was very good to do these tests today. and I'll get back to this before too long, and we'll go with a half-wave rectified signal and prove if those diodes were actually filtering the RCF right out of the circuit, right? Because that is a possibility too. I'm just kind of thinking that this is a special signal we're trying to move, and when we worked in specials and telecoms, I mean, you had to have a lot of the circuits were really persnickety, and if you put a data signal through like a load coil, well, it wouldn't work. It would just mess it right up so bad that the data wouldn't come out the other side. Anyways, that's it for October the 30th, 2018. Till next time. Bye-bye.